Imagine the largest structure in the entire universe, a vast, invisible web stretching across billions of light years, with glowing, radiant nodes where galaxies gather like cities connected by cosmic highways. This is the cosmic web, the fundamental architecture of our universe, and hidden within its brightest intersections are mysteries that defy everything we think we know. For centuries, we've looked up at the night sky and wondered about the stars, but what lies between them, the threads and nodes of this immense cosmic tapestry, holds secrets far stranger than we ever imagined. These luminous junctions aren't just beautiful, they're active, dynamic, and host to phenomena so bizarre that even our most advanced laws of physics seem to fall short when we try to explain them. Today, we're setting off on a journey into the heart of these mysterious nodes, exploring 25 of the most puzzling and breathtaking unexplained phenomena occurring within them. From strange gravitational anomalies and unexplained energy emissions to hints of unknown forms of matter and forces, each of these cosmic curiosities invites us to rethink our understanding of reality itself. This isn't just a tour of far-off wonders, it's an invitation to join a quest for knowledge, to stand at the edge of the known and peer into the profound mysteries that shape the cosmos. You'll witness how these intersections challenge not only science but our very perception of existence, urging us to imagine what might be possible in the deepest reaches of space. So settle in and open your mind to the extraordinary. What you're about to explore goes beyond astronomy or physics. It touches on the grand, unfolding story of human curiosity and our relentless drive to uncover the truths of the universe. Together, we'll venture into the glowing nodes of the cosmic web, where the laws of nature as we know them are not just bent, but sometimes broken, and where each discovery brings us closer to revelations that could forever change how we see our place in the cosmos. This journey is just beginning. Our journey into the unknown begins not with something exotic, but with something that should be utterly familiar, the very stuff you and I are made of. Ordinary matter, the protons and neutrons scientists call baryonic matter, is the building block of planets, stars, and galaxies. According to our most trusted cosmological models, we can make a very precise prediction for how much of this ordinary matter should have been created in the Big Bang. And when we add up everything we can see, all the stars, all the glowing gas, all the dust, we come up short. A huge portion of it, nearly half, is simply missing. This is the great cosmic inventory problem, and it's within the dense nodes of the cosmic web that this mystery becomes most pronounced. These nodes are the universe's metropolises, the grand intersections where thousands of galaxies are drawn together by gravity. You would expect these regions to be absolutely packed with baryons, yet when we look, the numbers don't add up. It's as if we've counted all the bricks needed to build a city, but when we arrive, entire neighborhoods are just gone. So where did it all go? One leading theory suggests this missing matter isn't truly missing. It's just hiding in plain sight. We might be overlooking vast reservoirs of incredibly hot, diffuse gas that floats in the spaces between galaxies. This gas is so tenuous and so scorching hot that it doesn't emit the light our telescopes are designed to detect. It's a cosmic stealth material, invisible to our current eyes on the sky. Another compelling idea points to the very nature of these nodes. They are chaotic, violent places where galaxies collide and tear each other apart, where supermassive black holes blast out unimaginable amounts of energy. This incredible violence might be physically ejecting normal matter, hurling it out into the vast, empty voids of the cosmic web where it becomes even harder to find. The nodes themselves could be both the gatherers and the scatterers of matter. This discrepancy forces us to question not just what we see, but how we see. It hints that our methods for taking the universe's census might be fundamentally flawed, that we are missing an entire phase of matter because we haven't yet learned how to look for it. Solving this puzzle is crucial because you can't understand the story of the cosmos if you don't know the main characters, and the missing baryons are a leading role we have yet to fully see. And if the mystery of our own missing matter wasn't perplexing enough, the nodes of the cosmic web present us with an even deeper and more fundamental puzzle, one that involves the very scaffolding of the universe itself, dark matter. We've long known that this invisible, mysterious substance makes up the vast majority of matter in the cosmos, acting as the gravitational glue that pulls galaxies together into these vast nodes. Our standard model of cosmology, built on the idea of cold dark matter, makes very specific predictions about how this unseen mass should be distributed. It should form incredibly dense, clumpy halos at the hearts of these galactic intersections, with its gravitational influence fading smoothly as you move outward. But what we're actually observing is starting to defy those expectations in startling ways. Recent observations, particularly from sophisticated gravitational lensing studies, are painting a bizarre and inconsistent picture. In some of these colossal nodes, dark matter appears to be clustered far more densely than our models allow. It's as if the invisible skeleton of the universe has developed unexpected knots, points of intense gravitational pull that warp the fabric of spacetime more severely than anyone predicted. The light from galaxies behind these nodes is bent and distorted into strange, stretched arcs, telling us that the mass there is concentrated in a way that simply shouldn't be possible. It's an overachievement of darkness, a gravitational anomaly that leaves theorists scrambling for an explanation. Conversely, and just as puzzlingly, other massive nodes show a distribution of dark matter that is strangely, almost unnaturally uniform. Instead of a sharp, dense peak at the center, the gravitational field suggests the dark matter is spread out more evenly, like a faint, diffuse fog rather than a concentrated core. This lack of central clustering directly contradicts the cold, collisionless nature of the dark matter particles we've hypothesized for decades. If dark matter is truly cold and only interacts through gravity, it should invariably sink to the center of these vast potential wells. The fact that it doesn't in so many cases suggests there might be something profoundly wrong with our basic assumptions. Perhaps dark matter isn't completely cold. Maybe it has some intrinsic property that allows it to interact with itself, creating a form of pressure that prevents excessive clumping. Or perhaps our understanding of gravity itself needs a fundamental revision on the largest scales. These anomalous distributions are more than just academic curiosities. They strike at the heart of our cosmological models. For decades, the cold dark matter paradigm has been the cornerstone of our understanding of structure formation. But these observations from the universe's largest junctions are presenting us with clear, empirical data that something is amiss. They are the cosmic equivalent of finding that the foundation of a skyscraper is behaving in a way no engineer's blueprint could ever account for. Each anomalous node is a clue, a piece of evidence that we are on the verge of a monumental discovery, one that could force us to rewrite the textbooks on the most abundant form of matter in the universe. But the gravitational oddities of dark matter are not the only enigmas these cosmic crossroads have to offer. As we probe deeper into these radiant hubs, we encounter a phenomenon of pure, raw energy that defies explanation, mysterious and intense bursts of gamma rays. These are not the gentle whispers of starlight. These are the universe's most powerful and violent explosions, the highest energy form of light, and they are pouring out of specific nodes in the cosmic web with no clear source in sight. This discovery comes primarily from the Fermi Gamma Ray Space Telescope, our most sensitive sentinel for this extreme radiation, which has been tirelessly scanning the heavens for over a decade. Its maps of the sky should, in theory, be a cosmic inventory of known high-energy engines, pulsars, the remnants of supernova, and the devastating jets from supermassive black holes. Yet, when scientists look at the data from these dense galactic intersections, they find a persistent and puzzling excess of gamma-ray light that doesn't align with any of these known celestial objects. It's as if you were listening to a symphony and could identify every instrument, the violins, the cellos, the trumpets, but then you hear a powerful, resonant note that doesn't belong to any instrument in the orchestra. That's what these gamma-ray emissions are, a cosmic note without an instrument. The signal is a diffuse, pervasive glow that seems to originate from the heart of the node itself, rather than a single, pinpoint location. This rules out obvious culprits like a lone, flaring black hole or a recently exploded star. The emission is collective, a signature of the entire environment, which makes its origin even more difficult to trace. One of the most thrilling and controversial hypotheses is that we are witnessing the final, fiery death throes of dark matter itself. The theory goes that when two particles of dark matter collide under the right conditions, they could annihilate each other in a spectacular burst of energy, converting their mass directly into gamma rays. The dense cores of these nodes, where dark matter is thought to be most concentrated, would be the perfect arenas for such a rare and catastrophic event. If this is true, then we are not just mapping the invisible stuff of the universe. We are watching it destroy itself, providing us with the first direct clue to its true particle nature. This would be a discovery of Nobel Prize-winning magnitude, finally cracking a mystery that has persisted for nearly a century. Yet, the universe is a place of immense complexity, and other, less exotic explanations are also on the table. This unexplained glow could be the collective output of countless astrophysical processes we already understand, just operating on a scale we've never before appreciated. For instance, these nodes are filled with a sea of high-energy particles called cosmic rays, which are constantly zipping through space at nearly the speed of light. When these particles interact with the sparse gas and light floating between the galaxies, they can produce gamma rays as a byproduct. The sheer scale and density of a node could amplify this process into a diffuse, uniform glow that our current models simply haven't accounted for. Alternatively, we might be seeing the combined output of thousands of faint, distant pulsars, the spinning corpses of dead stars, each too dim to see individually, but together creating a significant and unrecognized background hum of radiation. The true answer remains elusive, caught between the breathtaking possibility of a fundamental physics breakthrough and the more mundane, yet still profound, reality of collective astrophysical phenomena we have yet to fully catalogue. Each new observation from Fermi and other telescopes adds another piece to this high-energy puzzle, forcing us to refine our models and sharpen our questions. This mystery reminds us that even our most advanced instruments are still, in many ways, scratching the surface of the cosmos, and that the universe's brightest intersections still hold shadows where secrets can hide. And just as we grapple with the high-energy mysteries lurking in the nodes, we must turn our attention to the oldest light in the universe, a fossilized echo from the dawn of time that holds its own set of profound and startling secrets. This is the cosmic microwave background, the faint afterglow of the Big Bang itself, which blankets the entire sky. For decades, this radiation has been our most trusted map of the infant universe, a nearly perfect snapshot of its smooth, uniform state. But when we look more closely, this map is not as perfect as we once believed. Bizarre, large-scale patterns emerge, and they seem to be mysteriously linked to the positions of the cosmic web's largest nodes, suggesting a connection between the universe's birth and its present-day structure that defies all standard explanation. The most famous and controversial of these patterns is known as the axis of evil. This isn't a dramatic name for a celestial object, but a label scientists gave to a baffling alignment they found in the cosmic microwave background data. The temperature fluctuations in this ancient light should be completely random, like a static-filled television screen, with hot and cold spots scattered in no particular direction. Yet, the data reveals that these fluctuations appear to be aligned along a specific preferred axis in space. An axis that, unnervingly, also seems to align with the plane of our own solar system and the direction in which the cosmic web's most massive nodes are stretched out. It's as if the universe's largest structures today are whispering that they were somehow imprinted with a direction from a time before time, a pre-initial condition that should have been erased by inflation. This alignment is so statistically improbable and so philosophically unsettling that it has been a thorn in the side of cosmology for years. The standard model of cosmology relies on the principle of isotropy, the idea that the universe on a large scale looks the same in every direction and has no special center or axis. The axis of evil directly challenges this foundational principle. It implies a cosmic preferred direction, a grand asymmetry written into the fabric of reality at the moment of creation. One extraordinary possibility is that this axis is a scar, a relic from the universe's very first instance before the period of rapid inflation began. Perhaps the universe was not born perfectly symmetrical. Maybe it had a tiny initial twist or polarization that inflation magnified across the entire cosmos, leaving this faint directional imprint that later guided where the largest nodes of the cosmic web would form. Another, even more mind-bending hypothesis suggests that our universe might have collided with another universe in the multiverse during its infancy, an event that could have left a directional bruise on our cosmic microwave background. Or perhaps it points to something even more fundamental, that our understanding of gravity or the nature of space itself is incomplete on the largest possible scales. The correlation with the nodes deepens the mystery. These gravitational anchors, the largest structures we know, may not have formed randomly. Their positions and alignments could be dictated by this primordial blueprint, a hidden architecture established in the first fleeting moments after the Big Bang. This forces us to confront the possibility that the universe's entire history, from its first whisper to its current web of galaxies, was somehow directed or influenced from the very start. But as if a preferred axis in the afterglow of creation wasn't puzzling enough, the nodes of the cosmic web present us with a challenge that strikes at the very core of cosmic history, a timeline that seems physically impossible. Our universe is, by all accounts, ancient. It has had nearly 14 billion years to build its grandest structures. The process is a slow, gravitational dance. Tiny quantum fluctuations from the Big Bang are magnified by the relentless pull of dark matter, gradually gathering ordinary matter into the first stars, then galaxies, and finally, the massive clusters that anchor the cosmic web. This is the standard, patient story we've told for decades, a story with a clear and logical sequence. Yet, when we point our most powerful telescopes at the farthest reaches of space, and therefore the deepest reaches of time, we are finding colossal nodes that simply should not exist. They appear too early, fully formed in an era when the universe was far too young to have built them. These are not just slightly premature formations, they are cosmic impossibilities. Astronomers have discovered incredibly massive clusters of galaxies, shining like brilliant metropolises, at redshifts so high that the light we see from them left when the universe was less than a tenth of its current age. According to our most robust cosmological models, there simply hadn't been enough time for gravity to pull together such immense concentrations of matter. It would be like discovering a sprawling, 1,000-year-old oak tree in a forest that was only seeded a decade ago. The existence of such a tree would force us to completely reconsider how trees grow. In the same way, these precocious nodes force us to question the fundamental mechanisms of structure formation itself. One of the most famous examples is a galaxy cluster known as SPTCLJ03104647. The light from this behemoth has been traveling for over 13 billion years, meaning we are seeing it as it was when the universe was a mere 700 million years old, a cosmic toddler. Yet it contains the mass of hundreds of trillions of suns, already assembled into a gravitationally bound cluster. The standard model struggles mightily to explain how such a vast structure could coalesce so quickly. The gravitational pull of dark matter is powerful, but it is not instantaneous. It works at the speed of light, and the math shows that the process should have taken much longer. This presents a profound dilemma for cosmologists. It suggests that either the seeds for these structures were planted much earlier than we thought, perhaps in a period of hyperinflation so extreme it warped the very rules of gravitational growth, or that our understanding of gravity is incomplete on the largest scales. Some theorists have even explored the radical possibility that the strength of gravity itself was different in the early universe, allowing for a faster, more aggressive clumping of matter. Others look to exotic forms of dark matter that might interact with itself or with radiation in ways that would accelerate the formation of these cosmic giants. Each potential solution, however, requires bending or even breaking the very laws of physics we use to define the universe's evolution, pushing us toward a new paradigm where the cosmos can build its greatest wonders at a pace we once believed was forbidden. And just when we think we've reached the limits of cosmic strangeness, the nodes of the cosmic web present us with a phenomenon that seems to defy the very nature of space and time. A concept so bizarre it belongs to the quantum realm, but appears to be operating on the largest scales imaginable. This is the controversial and mind-bending idea of quantum entanglement stretching across billions of light years. In the subatomic world, quantum entanglement is a well-documented, though utterly strange, phenomenon where two particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously called it, challenges our classical understanding of locality and information transfer. But what if this spooky action wasn't confined to the tiny world of particles? What if the universe itself is entangled on a grand structural scale? This is not mere speculation. It arises from a specific and persistent statistical anomaly found in the large-scale structure of the universe. When cosmologists map the distribution of galaxies, they expect to find a certain degree of randomness. The positions of galaxy clusters should be independent of one another, especially if they are separated by vast cosmic voids. The gravitational influence of one node simply cannot reach another that is billions of light years away, as nothing, not even gravity, can travel faster than light. Yet, detailed analysis of surveys like the Sloan Digital Sky Survey reveals a faint but statistically significant correlation between the positions of extremely distant pairs of nodes. They appear to be ever so slightly aligned or connected in a way that cannot be explained by any known force or interaction that has had time to travel between them since the beginning of the universe. It's as if these separate metropolitan centers of the cosmic web are somehow in silent, instantaneous communication, their very existence subtly coordinated across unimaginable distances. The implications of this are staggering. If these correlations hold up to further scrutiny, they would suggest that the universe's largest structures retain a memory of a connection that existed before the expansion of space tore them apart. The most prominent theory attempting to explain this involves the inflationary epoch, that period of faster-than-light expansion in the universe's first fraction of a second. During inflation, regions of space that were once in causal contact close enough to influence each other were suddenly stretched far beyond each other's light horizons. The proposal is that quantum fluctuations present in that tiny, connected patch of the early universe became entangled, and as inflation blew up that patch to become our entire observable universe, those quantum correlations were imprinted onto the distribution of matter and dark matter. Essentially, the large-scale structure we see today could be a magnified, fossilized record of primordial quantum entanglement. The nodes aren't just gravitationally bound structures, they are quantum siblings, their fates linked since the dawn of time. Naturally, this idea is met with intense skepticism and vigorous debate within the physics community. Critics argue that these statistical correlations could be artifacts of the way we observe the universe or subtle biases in our mapping techniques. They point out that confirming a quantum effect on such a macroscopic scale requires ruling out every other conceivable astrophysical or cosmological explanation. The standard model of cosmology does an exceptionally good job of explaining the universe's structure without invoking non-local quantum connections, so the burden of proof for such a radical idea is incredibly high. Yet, the anomaly persists, a tantalizing hint that our understanding of physics might be incomplete, that the fundamental divide between the quantum world and the cosmic world may not be as absolute as we once believed. This potential discovery pushes at the boundaries of not just cosmology, but of philosophy itself. It suggests a universe that is profoundly interconnected in ways that transcend the familiar dimensions of space and time, a cosmos where here and there might not be as separate as they appear. If true, it would mean that the cosmic web is more than just a beautiful structure. It is a physical manifestation of the universe's deepest, most fundamental quantum nature, woven into the very fabric of reality on the grandest possible scale. While the idea of quantum connections spanning the cosmos stretches our imagination, some of the most visually striking mysteries are found not in theoretical correlations, but in enormous, ghostly structures that simply appear in our telescopes. In recent years, radio astronomers have been astonished by the discovery of vast, circular formations that seem to emerge from the very heart of the cosmic web's nodes. Structures so bizarre and unprecedented they've been officially named odd radio circles, or ORC. These are not subtle statistical anomalies. They are colossal, unmistakable rings of energy that can span hundreds of thousands of light years, often dwarfing the entire galaxies they appear to encircle. Their discovery was almost accidental, a triumph of modern sky surveys that map the universe in wavelengths invisible to the human eye. As telescopes like the Australian Square Kilometre Array Pathfinder scanned the heavens, they began picking up these perfect, circular emissaries that didn't correspond to any known type of object in optical catalogues. They were new, they were huge, and they were utterly perplexing. The defining characteristic of an ORC is its remarkable, almost artificial-seeming circular symmetry. In a universe where most structures are defined by chaotic, clumpy, or spiral forms, think of the irregular shape of a galaxy cluster or the elegant arms of a whirlpool galaxy. Finding something so perfectly round is immediately jarring. It suggests a sudden, spherical, and incredibly energetic event, a wave of energy that exploded outward in all directions with astonishing uniformity. Adding to the mystery is the fact that these circles are visible only in radio wavelengths. When astronomers point optical, infrared, or X-ray telescopes at the same coordinates, they often find nothing but empty space or a quiet galaxy at the very center, seemingly incapable of producing such a tremendous structure. It's like seeing the ripple from a pebble dropped in a pond, but without ever seeing the pebble itself, and where the ripple is larger than the pond. The energy signature of these ORCs is another piece of the puzzle that defies easy explanation. The radio emission has a specific polarization, indicating the presence of highly organized magnetic fields and energetic electrons spiraling around those field lines. This is a signature often associated with the aftermath of a colossal shockwave, but the scale is unimaginably larger than anything we've seen before. The most logical initial guess was that these were the remnants of a supernova explosion, but a typical supernova remnant is 1,000 times smaller. Perhaps it was the blast wave from a star that went supernova in an extremely dense environment, but the math never quite added up. Another early thought pointed to the end stages of a merger between two supermassive black holes, an event that would unleash gravitational waves and potentially a massive outflow of energy. Yet again, the sheer size and perfect spherical nature of the ORCs don't neatly fit this violent but messy process. The leading theories attempting to explain ORCs are as spectacular as the objects themselves. One compelling idea is that we are witnessing the aftermath of a truly gargantuan radio galaxy that has long since faded from view. In this scenario, a supermassive black hole at the center of a node would have had an active phase millions of years ago, shooting out twin jets of plasma at near light speed. If one of these jets was firing directly along our line of sight, pointing right at us, its lobe of radio emission would appear as a circular ring projecting onto the sky, an illusion of perspective. However, not all ORCs have a central galaxy that shows signs of such past activity, and the perfect circularity remains a challenge for this model. Another, more dramatic hypothesis suggests that ORCs are the visible shockwaves from a starburst event of incomprehensible proportions. Imagine not just a few stars forming, but an entire node of galaxies experiencing a synchronized, furious wave of star formation. The combined effect of millions of supernovae exploding in a relatively short cosmic time period could blow a spherical bubble of hot gas and relativistic particles into the intergalactic medium. This would create an expanding shell that we see as a radio circle. The energy required is almost beyond calculation, but the dense environments of cosmic web nodes are one of the few places in the universe where such a phenomenal burst of energy might be possible. Perhaps the most exotic theory ventures beyond known astrophysics, proposing that ORCs could be the throats of wormholes or the imprint of a collision between bubbles in the multiverse. While these ideas are captivating, they remain firmly in the realm of speculation without more concrete evidence. What makes ORCs so fascinating is that they are a completely new class of object, discovered not in the distant early universe, but right in our cosmic backyard. A reminder that even in the well-mapped territories of the modern cosmos, profound mysteries can still emerge, challenging us to rethink what we know about the most energetic processes shaping the universe's grandest structures. But perhaps the most unsettling challenge to our cosmic models comes from a fundamental measurement that should be the same no matter where you look: the expansion rate of the universe itself. For a century, we have operated under the principle of isotropy, the idea that the universe is uniform and looks the same in every direction. This is the bedrock of modern cosmology. A direct consequence of this is that the rate at which the cosmos is expanding, known as the Hubble constant, should be a single universal number. Whether you measure it by looking north, south, east, or west, the answer should always be the same. Yet, a growing body of evidence is now suggesting that this might not be the case, and the direction of this discrepancy appears to be mysteriously tied to the grand architecture of the cosmic web. This phenomenon is known as anisotropic Hubble flow. Anisotropic simply means directionally dependent, and Hubble flow refers to the recession of galaxies due to the expansion of space. In essence, it seems that galaxies are fleeing from us at slightly different speeds depending on which way we point our telescopes, as if the universe is stretching faster in some directions than in others. This isn't a small, marginal error. Some studies have pointed to variations that could be as high as several percent, a significant deviation that sends shockwaves through the field of cosmology. The most compelling evidence for this comes from painstakingly precise measurements of different types of celestial mileposts, like Type 1, a supernova, and the echoes of light around variable stars. When astronomers plot the velocities of these objects against their distances, the resulting expansion rate seems to depend on their location in the sky relative to the densest nodes and filaments of the cosmic web. One leading hypothesis for this bizarre directional bias points to the immense gravitational pull of these superclusters and nodes. We've long known that on local scales, gravity can overpower the expansion of the universe. Our own Milky Way is not expanding because it is gravitationally bound. The proposal is that the gravitational influence of these largest structures extends far beyond their visible boundaries, creating vast basins of attraction that can subtly tug on the motion of galaxies. In the direction of a supremely massive node, the expansion of space might be slightly slowed or resisted by this immense gravitational drag. Conversely, when we look out into the deep, empty cosmic voids, there is far less matter to counteract the pull of dark energy, potentially allowing space to stretch at a faster rate in those directions. From our vantage point, it would appear as though the expansion rate itself is changing based on the direction we look, a cosmic illusion created by our position within an uneven gravitational landscape. This idea of a Hubble tension related to large-scale structure is a radical departure from the perfectly smooth, homogeneous universe we've long assumed. It suggests that we may not live in a typical region of space, but rather in a somewhat unusual spot that skews our measurements. If true, it could provide an elegant solution to one of the biggest ongoing debates in cosmology: the disagreement between the measured value of the Hubble constant from the early universe derived from the cosmic microwave background and the value measured from local, modern-day observations. This discrepancy has puzzled scientists for years. Perhaps the local value isn't wrong, perhaps it's just local. Our measurement might be influenced by the specific gravitational environment of our galactic neighborhood, meaning we haven't been calculating a universal constant, but rather a regional one. This possibility forces a profound philosophical shift. The cosmological principle, which has guided our understanding for so long, may only be true on the very largest scales, while on the scale of the cosmic web, significant anisotropies and irregularities persist. The universe, in this view, is more like a complex ecosystem with currents and flows, rather than a perfectly uniform expanding balloon. Unraveling this mystery requires more than just better data. It demands that we precisely map our own position within the cosmic web and understand how the gravitational tides from the nearest giant nodes, like the Laniakea supercluster of which we are a part, are influencing our perspective on the entire cosmos. It is a humbling reminder that to truly see the universe, we must first understand our place within it. And if the universe's expansion rate isn't as constant as we thought, then our understanding of time itself might also be due for a revision, especially within the most powerful gravitational fields of the cosmic web's nodes. Einstein's theory of general relativity has been one of the most successful and thoroughly tested ideas in all of science. One of its most fascinating predictions is gravitational time dilation, the concept that time itself flows at different rates depending on the strength of the gravitational field. A clock placed close to a massive object will tick more slowly than a clock in the emptiness of interstellar space. We've confirmed this with exquisite precision here on Earth and within our solar system. But when we look out to the most massive structures in the universe, the nodes of the cosmic web, we are beginning to see hints that time might not be dilating in quite the way we expect, presenting anomalies that could point to new physics. These investigations rely on using the universe's most violent and predictable events as cosmic clocks. One key method involves studying Type 1, a supernova, the brilliant explosions of white dwarf stars that reach a very specific, predictable peak brightness. Because we know their intrinsic brightness, we can use them as standard candles to measure vast cosmic distances, but they also provide a unique way to measure the flow of time. The entire life cycle of these supernovae, from the initial explosion to their fading glow, follows a very reliable timeline. When one of these events occurs in an extremely massive galaxy cluster at the heart of a node, the intense gravity should slow down the apparent progression of the explosion from our distant vantage point. The supernova's light curve, its brightening and dimming should appear stretched out like a film being played in slow motion. And while we do see this time dilation effect, some studies have reported that the degree of slowing doesn't always perfectly match the predictions of general relativity based on the cluster's estimated mass. In some cases, the time dilation is slightly weaker than expected, as if the gravitational grip of the node isn't quite as strong as our models suggest, or as if time itself is more resistant to being stretched than we thought possible. Even more puzzling data comes from the study of quasars, the incredibly luminous cores of distant galaxies powered by supermassive black holes. These engines are not as orderly as supernova. Their light output can fluctuate wildly and unpredictably over time. However, by analyzing the light curves of thousands of quasars residing within the same massive node, astronomers can perform a statistical trick. They can stack and average these erratic signals, looking for a consistent pattern of time dilation that should correlate with the immense gravitational potential of their environment. Recent analyses have revealed a strange signal. The variability in the light from these quasars appears to be stretched in a way that suggests time is flowing more slowly, but the amount of dilation, once again, doesn't always align with the mass we calculate for the node. It's as if the gravitational field in these ultra-dense regions has an extra component we haven't accounted for, something that is subtly altering the fabric of spacetime itself. So what could be causing this discrepancy? One possibility is that our estimates for the total mass of these nodes are simply incorrect. Perhaps there are vast amounts of hidden mass, either ordinary matter in a form we cannot detect or an unusual distribution of dark matter that is subtly altering the gravitational potential and thus the predicted time dilation. Another, more radical idea is that our understanding of gravity itself needs modification in these most extreme environments. Theories like modified Newtonian dynamics, or MUND, which seek to explain galactic rotation without dark matter, have been extended to cosmological scales in proposals like modified gravity. These theories predict subtle differences in how gravity behaves in the weakest fields, which could manifest as an altered time dilation effect within the extensive but diffuse gravitational field of a massive cluster. Perhaps the most mind-bending explanation involves the very nature of dark energy. We think of dark energy as a force causing the expansion of empty space, but what if it also interacts with gravity in a way that weakens time dilation in regions of high density? Or maybe these anomalies are a hint that constants of nature, which we assume are fixed across time and space, could actually vary in different gravitational environments. The fine structure constant, which governs the strength of electromagnetic interactions, has been proposed to vary in strong gravitational fields, which could indirectly affect how we perceive the passage of time in light from these distant objects. Each observation of these temporal anomalies forces us to question the most fundamental pillars of physics, suggesting that the cosmic web's nodes are not just places of immense matter and energy, but also natural laboratories for testing the absolute limits of Einstein's theory and perhaps discovering what lies beyond it. Moving from the subtle distortions of time, we encounter another deeply puzzling feature of the cosmic web's nodes: the presence of immense, organized magnetic fields that stretch across millions of light years. We typically think of magnetic fields as localized phenomena, the kind that wrap around a planet, flow through a star, or are generated by the churning core of a galaxy. But within the largest intersections of the cosmic web, astronomers have detected magnetic fields of incredible coherence and scale. Fields that are not confined to any single galaxy, but instead permeate the entire vast space between them, connecting hundreds of galaxies within a node as if they were all threaded on the same invisible lines of force. The sheer size and strength of these fields present a monumental puzzle because we simply don't have a complete explanation for how they could have formed or what cosmic battery could possibly sustain them. The discovery of these fields is a testament to our ingenuity in observing the invisible. We can't see magnetic fields directly, but we can see their effect on the high-energy particles that fill the space within a node. As electrons, accelerated to nearly the speed of light, travel through these vast regions, they spiral along the magnetic field lines. This spiraling motion causes them to emit synchrotron radiation, a specific type of radio wave that tells us not only that a magnetic field is present, but also allows us to map its direction and estimate its strength. What these maps reveal is astonishing. In some of the universe's largest nodes, the magnetic fields are not chaotic or tangled. They show a surprising degree of order and alignment over scales that can exceed 10 million light years. It's the difference between the random iron filings scattered around a small magnet and the immense structured magnetic field that encompasses the entire Earth. The scale is almost incomprehensible. The central mystery is the origin of these fields. The leading theory for cosmic magnetism is known as the dynamo effect. The idea is that a weak seed magnetic field, perhaps generated in the early universe, can be amplified and organized by the motion of conducting fluids like the ionized gas within a galaxy. Over billions of years, the rotation and turbulence of a galaxy can take a faint primordial field and stretch, twist, and strengthen it into the powerful fields we observe today. This theory works beautifully to explain the magnetism within individual galaxies, but it completely falls apart when applied to the intergalactic medium within a node. The gas out there is incredibly thin, a near-perfect vacuum by Earth standards, with particles so spread out that they might only collide once every few million years. There is simply not enough continuous, organized motion in this diffuse environment to power a dynamo effect on such a colossal scale. It would be like trying to power a city's electrical grid with a single, tiny battery. The energy source is utterly inadequate for the task. This leaves scientists with a profound chicken and egg problem. If the dynamo effect can't create these fields from scratch, then they must have been born large. This points to a primordial origin, suggesting these vast magnetic fields were somehow woven into the fabric of space-time in the universe's earliest moments. One compelling hypothesis is that these seeds were created during the epoch of inflation, that period of faster-than-light expansion just after the Big Bang. Quantum fluctuations during this hyper-accelerated phase could have generated weak magnetic fields that were then stretched across cosmic scales by inflation itself, imprinting a coherent magnetic blueprint onto the future locations of the cosmic web. If this is true, then the magnetic fields we see today in the nodes are fossilized relics, ancient whispers from the birth of the cosmos that have persisted for over 13 billion years. Yet, the survival of these fields for so long is its own mystery. The intergalactic plasma within a node is not completely still. It is stirred by the gravitational tides of merging galaxies, shock waves from supernova explosions, and the powerful jets from supermassive black holes. These violent motions should have tangled, diluted, and dissipated any primordial field beyond recognition over the age of the universe. The fact that we still see coherent fields means something must be actively maintaining them, or that they are far stronger and more resilient than our current physics can account for. This has led to other, more exotic theories. Some researchers suggest that these magnetic fields could be a manifestation of something entirely new, perhaps linked to dark matter or dark energy. If dark matter particles possess even a tiny electric charge, their collective motion could generate magnetic fields on a gigantic scale. Or the fields could be a side effect of fundamental flaws in the fabric of spacetime itself, a concept arising from certain string theory models. The existence of these immense magnetic forces is more than just a curiosity. It has a dramatic effect on the evolution of the node itself. Magnetic fields can influence how gas cools and collapses to form new stars. They can channel and focus the incredible jets from black holes, and they can regulate the flow of heat and cosmic rays throughout the intergalactic medium. A complete understanding of how these giant intersections of galaxies live and die is impossible without first solving the mystery of the magnetic forces that bind them. They are an invisible architecture, a hidden framework that shapes the visible universe in ways we are only beginning to perceive, challenging us to find the source of magnetism on the grandest of scales. Just when we thought we had mapped the limits of cosmic weirdness, the universe presents us with a soundtrack written in the fabric of spacetime itself, a low, universe-wide hum of gravitational waves. These ripples, first predicted by Einstein, are caused by the most violent events in the cosmos, colliding black holes and merging neutron stars. For years, we've been listening for the individual, loud crashes of these events with observatories like LIGO and Virgo. But recently, we've begun to hear something else entirely. A background rumble, a collective chorus of countless gravitational waves overlapping from all directions, creating a persistent hum that fills the entire universe. This is the gravitational wave background, and its emerging pattern holds a staggering secret. This faint signal isn't random noise. It appears to be mysteriously, inexplicably correlated with the positions of the largest nodes in the cosmic web. It's as if the universe's grandest structures are singing in harmony with the echoes of its most violent collisions. This discovery comes from an ingenious cosmic instrument known as a pulsar timing array. Rather than building a single, massive detector on Earth, astronomers use the galaxy itself as an observatory. They monitor a network of pulsars incredibly dense, spinning neutron stars that act as nature's most precise metronomes, sending out beams of radio waves with a rhythm more accurate than any atomic clock. As a gravitational wave passes through the space between us and one of these pulsars, it minutely stretches and compresses space-time, causing a tiny, temporary shift in the timing of the pulsar's ticks. By carefully monitoring an entire array of these celestial clocks scattered across the galaxy, scientists can detect the subtle fingerprint of a passing gravitational wave background. The latest data from collaborations like NanoGrav, the European Pulsar Timing Array, and others have not only confirmed this background hum, but have also begun to map its intensity across the sky. And this is where the mystery truly deepens. When astronomers compare this map of the gravitational wave background to maps of the cosmic web's most massive nodes, they find a startling and unexpected correlation. The hum seems to be slightly louder, more pronounced, in the directions of these immense galactic intersections. The regions of space that are already the most overdense, gravitationally powerful places in the universe are also the sources of a stronger gravitational wave signal. On the surface, this makes a kind of intuitive sense. These nodes are where galaxies and their central supermassive black holes are packed together most tightly, making them the most likely venues for the colossal mergers that create gravitational waves. But the standard models of galaxy formation and evolution suggest that the distribution of these merging events should be far more uniform. The strength of the correlation we are seeing is stronger than our simulations predict, suggesting that something is supercharging the production of gravitational waves within these specific environments. So what could be causing this supercharged symphony? One compelling possibility is that the nodes are hosting a far greater number of merging supermassive black holes than we ever imagined. At the heart of nearly every large galaxy lies a supermassive black hole, and when galaxies collide and merge within a node, a common occurrence in these crowded neighborhoods, their central black holes are destined to eventually spiral together and combine in a cataclysm that shakes the very foundations of spacetime. The gravitational waves from a single one of these mergers would be immense, but the combined chorus from thousands of such pairs, all merging at different times, could create the persistent hum we detect. The enhanced correlation suggests that the processes driving these black holes together, the dynamics of gas and stars in the uniquely dense environment of a node, are far more efficient than our theories account for. Another, more exotic theory ventures beyond known astrophysics. Perhaps the gravitational wave background isn't solely produced by black hole mergers. Some cosmologists have proposed that this signal could be partially primordial, a relic from the universe's birth. The theory of cosmic inflation suggests that the rapid expansion of the infant universe could have generated a storm of gravitational waves that still echo throughout the cosmos today. If this is true, the correlation with the nodes could be a profound clue that the seeds for these largest structures were planted by these primordial waves themselves. The gravitational waves from inflation would have subtly influenced the distribution of matter in the early universe, meaning the nodes formed exactly where the primordial gravitational wave energy was strongest. In this scenario, the correlation isn't a coincidence. It's a direct lineage, a cosmic family connection between the first vibrations of space-time and the largest structures we see today. Unraveling this mystery is more than an academic exercise. Pinpointing the exact source of this correlated hum is the key to understanding the population and behavior of the most massive black holes in the universe, objects that are otherwise invisible until they merge. It also provides a completely new way to probe the era of inflation, offering a window into the highest energies possible, energies that even the Large Hadron Collider could never hope to reach. The gravitational wave background is a new sense with which we can perceive the cosmos, and its mysterious link to the cosmic web is telling us a story about the universe's past and present that we are only just beginning to understand. Now we arrive at a mystery rooted in one of astronomy's most fundamental tools, the redshift of light. For a century, we've used redshift as our primary yardstick for measuring the universe. It's the Doppler effect for light. As a galaxy moves away from us, its light is stretched toward the red end of the spectrum, and the faster it recedes, the redder it appears. This principle isn't just how we measure distance, it's how we map the cosmos, charting the positions and motions of thousands of galaxies to reconstruct the grand architecture of the cosmic web. Within the bustling nodes of this web, however, this reliable law appears to break down in bizarre and unexpected ways, revealing motions that defy our understanding of gravity's pull. When we point our telescopes at a massive galaxy cluster at the heart of a node, we expect to see a specific pattern in the redshifts of its member galaxies. The cluster's immense gravity should hold sway over everything within it, meaning the galaxies should all be moving together in a somewhat organized, predictable way as they orbit the cluster's center of mass. Their velocities relative to the cluster's average should follow a smooth, statistical distribution, like a swarm of bees buzzing around a hive. Yet, when astronomers perform detailed spectroscopic analyses of these clusters, they often find something far more chaotic and perplexing. The redshifts are distributed in strange clumps and streams, with groups of galaxies moving with shared, peculiar velocities that don't align with the overall gravitational field of the cluster. It's as if, within the larger swarm, there are smaller squadrons of bees flying in tight formation on their own secret mission, ignoring the general flow of the hive. This phenomenon points to what astronomers call peculiar velocities, motions that are above and beyond the simple, smooth expansion of the universe. These aren't random twitches, they are coherent flows of dozens, sometimes hundreds, of galaxies all moving in the same direction at unusually high speeds. The most famous example of this on a slightly smaller scale is the so-called dark flow, a controversial observation that suggested entire clusters were drifting in a preferred direction, as if being tugged by something massive far beyond the observable horizon. Within the nodes, we see a more localized but equally startling version of this. Galaxies are streaming into or out of these dense regions at velocities that our models of the cluster's mass simply cannot account for. The gravitational pull of the visible matter and the estimated dark matter halo should not be strong enough to produce such rapid and organized infall, nor should it be able to accelerate galaxies to such high speeds as they are ejected. So what unseen force is orchestrating this chaotic dance? The immediate suspicion falls on the possibility of hidden mass. Perhaps our inventory of the dark matter within these nodes is even more incomplete than we thought. There could be vast, dense clumps of dark matter subhalos within the main halo that we cannot see, whose gravitational influence is whipping these galaxies into unexpected motions. Alternatively, the node itself might be part of a much larger, previously unrecognized flow pattern within the cosmic web. The gravitational pull from an adjacent supercluster, a structure of almost unimaginable size and mass just beyond our current maps, could be exerting a tidal force on the entire node, shepherding galaxies within it into these anomalous streams. The most radical explanation, however, challenges the force of gravity itself. For decades, a minority of physicists have championed theories like modified Newtonian dynamics, or MUND, which proposes that on very large scales and in very weak gravitational fields, gravity behaves differently than Einstein's general relativity predicts. It requires no dark matter. Instead, it modifies the equations of motion. While standard MUND has had successes explaining rotation curves of individual galaxies, its application to the colossal scales of galaxy clusters has been problematic. Yet, these anomalous redshift distributions and peculiar flows within nodes are exactly the kind of phenomena that modified gravity theories might be able to explain. They predict that in the extensive outer regions of a cluster, where the gravitational field is very weak, the acceleration of objects could be slightly different than standard models allow, potentially producing the kind of coherent flows we are observing. Each of these galaxies, with its anomalous redshift, is a data point in a grand cosmic argument. They are evidence that either our census of the universe's mass is still woefully inadequate, missing enormous hidden structures, or that our fundamental understanding of gravity, the force that literally holds the cosmos together, is in need of a serious revision. Unraveling this mystery requires ever more precise maps of the motions within these nodes, creating a 3D dynamical model of their chaos. It's a painstaking process, but it holds the key to determining whether we need to search for more dark matter or start rewriting the laws of physics. This deepening of the missing satellite problem within the nodes points toward a potential crack in the very foundation of our cosmic model. If dark matter is as cold and collisionless as we believe, these dense environments should be the most fertile grounds for the formation of small-scale structure. The fact that they are instead the most sterile places for dwarf galaxies is a paradox that demands a radical re-examination of our assumptions. One compelling line of thought suggests that our understanding of dark matter itself might be the issue. The standard cold dark matter model posits particles that interact only through gravity, allowing them to form those incredibly dense, numerous subhalos. But what if dark matter isn't completely cold? What if it has just a tiny bit of warmth or a slight ability to interact with itself or with other particles? This idea, known as self-interacting or warm dark matter, could provide an elegant solution. In these models, the dark matter particles would have a small amount of thermal motion or would collide with each other, effectively smoothing out the smallest, densest clumps. The immense gravitational tides within a node would then easily shred these warmer, less concentrated subhalos, preventing them from ever attracting enough gas to form a visible dwarf galaxy. It's a compelling idea, but one that requires delicate tuning to still explain the large-scale success of the cold dark matter model while fixing its small-scale failures. Yet, the answer may not require new physics at all, but rather a fuller appreciation of the sheer astrophysical violence that defines these cosmic metropolises. The environment within a massive node is extraordinarily hostile to fragile systems like dwarf galaxies. We must consider the dramatic effects of ram pressure and tidal stripping on a scale we rarely see elsewhere. As a small, dark matter subhalo and its associated gas attempts to orbit within the node, it doesn't travel through empty space. It plows through a hot, dense, and unforgiving atmosphere of intracluster plasma. This acts like a cosmic wind, brutally scouring away the gas reservoir that is the lifeblood of star formation. This process, known as ram pressure stripping, can effectively gut a dwarf galaxy before it even has a chance to properly form, leaving behind a dark matter ghost that is completely invisible to our telescopes. Simultaneously, the relentless gravitational tides from the massive central galaxy and the overall cluster potential constantly stretch and compress these small halos, pulling them apart in a process called tidal stripping. This can tear away not only their gas but even their stars and dark matter, dissolving the nascent galaxy entirely or leaving behind a faint, barely detectable stream of debris. Furthermore, the nodes are the domains of the most supermassive black holes, which often enter extremely active phases, flooding the entire intracluster environment with intense radiation. This radiation can heat the gas within incoming subhalos, preventing it from cooling and collapsing to form stars in the first place, a process known as cosmic feedback on a truly grand scale. It's a cosmic catch-22. The very conditions that create the deepest gravitational wells for dark matter to clump also create the most effective mechanisms for destroying the visible galaxies that should form within them. The nodes may not be missing their satellites after all. They may simply have efficiently and utterly destroyed them, leaving behind a dark, silent graveyard of failed galaxies. These gravitational and environmental explanations offer compelling solutions, yet they leave us with a profound question about the very rules of the game, a question that finds its sharpest focus not in what's absent, but in what's present specifically, in the chemical fingerprints of the elements that make up the thin, hot plasma bathing these nodes. When we analyze the light from this intracluster medium, we are essentially taking a core sample of the node's history, a record of every supernova explosion and stellar wind that has enriched it over billions of years. According to our detailed models of stellar evolution and nucleosynthesis, the processes that create elements inside stars, we expect to see a certain predictable pattern. Heavier elements like iron, silicon, and oxygen should be present in specific ratios, a cosmic signature of the specific types of stars that lived and died within the cluster's galaxies. But the universe, it seems, has been keeping a different set of books. The data reveals a chemical anomaly that is both subtle and staggering. In the hearts of many massive nodes, the abundance of certain elements, particularly iron, does not match our predictions. In some cases, the iron content is significantly higher than our models can account for. It's as if we've studied a city's industrial output for decades, carefully tracking every factory and its production, only to do an environmental survey and discover that there's twice as much steel in the ground as there should be. The immediate suspect is a higher rate of Type 1a supernova, the titanic thermonuclear explosions of white dwarf stars that are the universe's primary forges of iron. These events should have seeded the intracluster medium with this specific elemental signature, but to produce the surplus we observe, the rate of these explosions would have had to be vastly higher in the past than anything we see in galaxies today, a period of such incredible stellar violence that it challenges our understanding of how galaxies evolved within these dense environments. The plot thickens when we look at other elements. The ratio of certain elements to iron, such as oxygen or chromium, sometimes shows unexpected variations. This is a critical clue because different types of stellar deaths produce different elemental recipes. The core collapse supernova of massive stars are rich in oxygen, while Type 1a supernova are prolific iron producers. An anomalous ratio suggests that the balance of power between these two cosmic factories was different within nodes than it was in the more isolated field galaxies we often use to calibrate our models. Perhaps the extreme density of the node environment triggered a unique mode of star formation, favoring the birth of either very massive stars that died quickly in core collapse explosions or binary star systems that were more prone to becoming Type 1a supernova. The environment itself may have rewritten the rules of stellar life and death. One of the most fascinating and controversial ideas to explain these anomalies involves the very first stars in the universe, known as population 3 stars. These hypothetical behemoths, hundreds of times more massive than our Sun, are thought to have lived fast and died furious, ending their lives in spectacular explosions known as pair instability supernova. These events would have forged elements in a uniquely different pattern from the supernova we observe today, enriching the primordial gas from which subsequent generations of stars and galaxies formed. It's possible that the nodes, acting as gravitational traps, captured and retained a greater proportion of this pristine, pop Roman 3 enriched gas early on. The chemical oddities we see today could therefore be the faded fossil record of these first stars, a signature preserved for billions of years in the high-pressure environment of the node, isolated from the more well-mixed gas elsewhere in the cosmos. We would be witnessing the elemental legacy of the universe's very first fireworks, a chemistry set that has been out of production for over 13 billion years. Yet another possibility points the finger at the supermassive black holes that reign at the center of these nodes. Their relativistic jets, capable of injecting enormous energy into the surrounding medium, might also be directly contributing to nucleosynthesis. The extreme conditions within these jets, immense temperatures and densities, could potentially provide a site for exotic nuclear reactions that create elements in unusual proportions, a form of high-energy alchemy that our current models of stellar physics simply don't include. The nodes, it seems, are not just passive collectors of cosmic history. They may be active and unexpected participants in the periodic table, challenging us to expand our understanding of where and how the elements of life are truly made. But the strange elemental signatures within the nodes are not the only fingerprints of extreme violence we find there. Pouring out from these cosmic intersections is a rain of particles carrying energies so immense they defy the very laws of physics as we understand them. These are ultra-high-energy cosmic rays, subatomic bullets, often single protons hurtling through space with the kinetic energy of a well-thrown baseball, all compressed into a single fundamental particle. For decades, their origin has been one of astrophysics' greatest mysteries, because particles with such unbelievable energy should not be able to travel very far through the universe without losing it. Yet, when we finally began to map their arrival directions with observatories like the Pierre Auger Observatory, a sprawling detector array in Argentina that covers an area the size of Rhode Island, a bizarre and shocking pattern emerged. These cosmic cannonballs are not arriving randomly from all directions. They show a distinct and puzzling preference, a statistical anisotropy that seems to point back toward the locations of the most massive nodes in the cosmic web. This discovery upends a fundamental expectation. A proton carrying such an astronomical amount of energy is immensely susceptible to the pervasive sea of cosmic microwave background radiation, the leftover glow from the Big Bang. As it travels across millions of light years, it should constantly collide with these low-energy photons, a process that rapidly saps its energy in what's known as the GZK cutoff. This means any ultra-high-energy cosmic ray we detect must have originated from a source relatively nearby in cosmic terms, within about 250 million light-years. And within that local volume of the universe, the most prominent and powerful structures are the very nodes and superclusters we've been discussing. The correlation is undeniable. The highest energy events are not coming from random voids, but are statistically aligned with the directions of known colossal structures like the Virgo cluster or the Centaurus supercluster. It's as if the universe's largest gravitational anchors are also its most powerful particle accelerators, far outstripping anything we can build on Earth. The million-dollar question is, what engine within these nodes is capable of such a feat? To accelerate a single proton to such a mind-boggling energy requires conditions of almost unimaginable violence and precision. The leading candidate has always been the relativistic jets blasting from active supermassive black holes. These jets, composed of plasma moving at a fraction of the speed of light, could act as natural particle accelerators on a galactic scale. However, when we look at the specific nodes correlated with these cosmic rays, we don't always find a black hole in an obviously active, flaring state. This suggests the acceleration mechanism might be more complex, or that our understanding of black hole activity is incomplete. Perhaps the acceleration isn't happening in a single dramatic event, but is a cumulative process, with particles gaining a little bit of energy each time they cross a shock wave within the turbulent environment of the node, like a pinball being bounced between bumpers until it's launched at incredible speed. Another, more provocative idea is that we are seeing the decay products of something even more exotic. Some theories propose that these ultra-high-energy particles are not protons, but the result of super-heavy dark matter particles decaying at the hearts of these nodes. Since dark matter is thought to be most densely concentrated in these regions, it would be the natural place for such rare, catastrophic particle decays to occur, releasing a burst of energy that manifests as the cosmic rays we detect. This would directly tie the mystery of cosmic rays to the mystery of dark matter, suggesting that by studying these particles, we might be indirectly studying the properties of the universe's most elusive substance. The directional preference itself adds another layer of intrigue. It's not a perfect pinpointing, it's a broad statistical correlation. This could be due to the deflecting effect of interstellar and intergalactic magnetic fields. A proton, being electrically charged, doesn't travel in a straight line. It gets bent and twisted by the magnetic fields that permeate space, making it incredibly difficult to trace its path back to its exact source. The fact that we see any correlation at all is a testament to the sheer power of the sources. Their signal is so strong that it shines through the scrambling effect of cosmic magnetism. This also implies that the magnetic fields within and around these nodes might be even more complex and powerful than we currently model, acting not just as a barrier but perhaps as a focusing lens, channeling these particles in specific directions across the cosmos. Each detected cosmic ray is therefore a messenger carrying not just information about its source, but also a map of the magnetic highways it traveled to get here, if only we could learn to decode it. For decades, the story of cosmic structure seemed to focus on the bright, dense nodes where galaxies congregate, treating the vast, empty voids between them as little more than passive backdrops, the empty stages upon which the cosmic drama unfolds. But this view is rapidly changing, revealing a relationship far more dynamic and strange than anyone imagined. We are discovering that these voids are not simply empty. They are active players in the cosmic story, exerting a mysterious gravitational and evolutionary influence on the nodes themselves, a push and pull that challenges the very foundations of how we believe structure forms in the universe. This revelation begins with a counterintuitive gravitational truth. According to Einstein's general relativity, gravity is not just a force of attraction, it is also shaped by the absence of mass. A vast, underdense region like a cosmic void creates a unique kind of gravitational landscape. While the massive nodes pull matter inward, the empty voids effectively push it away. Imagine a vast hill in the fabric of spacetime, with the nodes being the deep valleys. Matter naturally wants to roll down into the valleys, but the expansive hills of the voids create a gentle, repulsive gradient. This means that the development of a massive node isn't just governed by its own immense gravity. It is also being subtly shaped by the overwhelming emptiness that surrounds it. The void acts as a cosmic repulsor, shepherding matter toward the nodes and influencing the very direction from which galaxies fall into the cluster. This gravitational interplay leads to one of the most peculiar observed phenomena: coherent flows of galaxies on unimaginably large scales. Astronomers mapping the motions of galaxies have found that entire nodes and the galaxies within them are often drifting in a particular direction with a shared velocity. This isn't the random motion of individual objects, it's a collective flow, as if the entire structure is being tugged by an unseen hand. The source of this tug is now believed to be the gravitational influence of the voids themselves. The sheer size and emptiness of a neighboring void can exert a tidal force on a node, pulling it and its constituent galaxies in a specific direction. In a very real sense, the nothingness is directing the motion of the somethingness, guiding the growth and evolution of the universe's largest structures in ways our models are only beginning to quantify. The influence of voids extends beyond mere motion, directly impacting the internal evolution of the nodes they border. The environment within a node that sits at the edge of a colossal void is fundamentally different from one that is surrounded by other dense structures. For galaxies on the void-facing side of a node, their experience is unique. They are being fed by infalling material that has traveled across millions of light-years of near emptiness, a journey relatively free from the disruptive encounters and turbulence that define the crowded interior of the node. This pristine, cold gas stream can fall onto these frontier galaxies more smoothly, potentially leading to different modes of star formation and evolutionary histories compared to their siblings on the node's crowded interior. This void-node interaction may even provide a key to unlocking one of cosmology's other great puzzles, the nature of dark energy. The accelerated expansion of the universe is driven by dark energy, and this expansion happens fastest in the emptiest regions, the voids. As voids grow larger and emptier over time, their repulsive gravitational effect intensifies. This creates a fascinating feedback loop. The expansion of the universe stretches the voids, which in turn exert a stronger influence on the nodes, which affects how galaxies flow and clusters merge. Some theorists propose that by meticulously studying the precise dynamics of how nodes and voids evolve in relation to each other, we might find a signature that distinguishes between a constant dark energy and more exotic models where its strength changes over time or in different environments. The silent, empty voids could be whispering the secrets of the force that will ultimately determine the fate of the entire cosmos. And as we chart the immense flows of matter and energy shaped by the vast emptiness of the cosmos, we are compelled to look even deeper into the very fabric of spacetime within the nodes, where the universe's most fundamental laws may be revealing their incomplete nature. The immense gravitational fields at the heart of these intersections create conditions so extreme that they might be unlocking a realm of physics we have never directly observed, the quantum nature of gravity itself. For decades, the greatest unsolved problem in theoretical physics has been the marriage of Einstein's general relativity, which governs the very large, with quantum mechanics, which governs the very small. These two pillars of modern physics are mathematically incompatible, and a unified theory of quantum gravity has remained elusive. Yet, within the chaotic, high-energy environments of the cosmic web's nodes, some researchers believe there are tantalizing signatures, subtle anomalies in the behavior of particles and energy that could be our first empirical glimpses into this hidden quantum realm. One of the most compelling places to search for these signatures is in the way light and particles behave as they traverse the intense gravity of a node. According to general relativity, the path of a photon is bent by gravity in a very precise and predictable way, a phenomenon we use every day in the science of gravitational lensing. However, some observations of highly distorted background galaxies reveal minuscule, additional fluctuations in their light that cannot be accounted for by the smooth gravitational field predicted by our standard models of dark matter. It's as if the fabric of spacetime itself has a faint, pixelated graininess at the smallest scales, a subtle shimmering effect that could be the result of spacetime being fundamentally quantized. This idea proposes that space is not infinitely smooth, but is instead composed of tiny, discrete units, a foam-like structure at the Planck scale, a size a billionth of a billionth of a billionth of a centimeter. Normally, this granularity is utterly invisible, but the immense gravitational magnification of a node might be acting like a cosmic microscope, amplifying these quantum effects to a level we could potentially detect. The anomalous flickering in strongly lensed images could be the light waves interacting with this proposed spacetime foam, a direct signature of quantum gravity at work. Beyond the behavior of light, the distribution of the highest energy particles within a node might also hold a key. Certain quantum gravity models predict that the inherent graininess of spacetime could violate a fundamental tenet of Einstein's special relativity, Lorentz invariance. This principle states that the laws of physics are the same for all observers, regardless of their constant velocity or direction. If spacetime is granular, it would provide a preferred frame of reference, meaning that the energy of a particle could very slightly depend on its direction of travel or its polarization. Within a node where particles are accelerated to incredible energies by black holes and shock waves, this effect could be magnified. Scientists are meticulously analyzing the energy spectra and arrival directions of ultra-high-energy cosmic rays and gamma rays that originate from these regions, searching for any statistically significant deviation that would indicate these particles experienced a slight energy loss or speed change due to the quantum structure of spacetime on their long journey to us. Finding such a deviation would be a monumental breakthrough, providing the first experimental evidence that we live in a quantum gravitational universe. The extreme densities at the cores of these nodes might also be creating conditions where the very concept of a localized particle breaks down. Some approaches to quantum gravity, like string theory, suggest that under such immense pressure, particles could exhibit non-local behavior, their identities becoming smeared or delocalized in a way that is fundamentally different from standard quantum mechanics. This could manifest as anomalies in the way energy is distributed in the hot plasma of the intracluster medium, with certain pockets of gas appearing slightly hotter or more energetic than our astrophysical models can explain, as if energy were appearing or disappearing from one point to another without a clear cause. It's a faint signal buried in a sea of complex thermal dynamics, but it represents a potential fingerprint of physics operating beyond the classical realm. Naturally, the search for these effects is fraught with immense challenges. Every proposed signature of quantum gravity has a plethora of more conventional astrophysical explanations. That anomalous flickering in a lensed galaxy could be caused by small, unseen clumps of dark matter. The subtle shifts in particle energies could be the result of complex magnetic field interactions we haven't fully modeled. The search, therefore, is not for a single smoking gun, but for a consistent pattern of anomalies that appear across many different nodes and that persistently defy all standard astrophysical interpretations. It requires a level of precision in our observations and a depth in our simulations that we are only now beginning to approach. The nodes of the cosmic web, with their unparalleled gravitational might, are acting as the universe's most powerful natural laboratories, offering us a unique vantage point to peer into the quantum foundations of reality itself. They challenge us to look beyond the smooth curves of general relativity and into the shimmering, chaotic, and potentially grainy heart of spacetime, where the true unified theory of everything may be waiting to be discovered. At the very heart of these galactic metropolises, anchoring the immense gravity of the nodes, lies another profound mystery that challenges our understanding of cosmic powerhouses, the supermassive black holes themselves. We've long assumed that the behavior and characteristics of these gravitational monsters would follow a predictable pattern based on the environment they inhabit. After all, a node is the ultimate cosmic feeding ground, a place brimming with gas, stars, and other galaxies, offering a near-limitless buffet for a growing black hole. Yet, when astronomers take a detailed census of these black hole populations, the statistics reveal a story that is anything but straightforward, pointing to formation and growth mechanisms we have yet to comprehend. The first glaring anomaly is their mass distribution. The standard model suggests that black holes in the densest environments should be the most massive, having gorged themselves on the abundant material over billions of years. While it's true that the single central black hole in a node's core galaxy is often the largest we know of, the overall population of black holes within the entire node tells a different tale. There appears to be a surprising shortage of intermediate mass black holes, the crucial missing link between the stellar mass black holes born from dying stars and the supermassive behemoths. This is the black hole equivalent of a city having plenty of modest homes and one gigantic skyscraper, but very few large mansions in between. It suggests that the growth process within nodes is incredibly efficient for the central black hole, perhaps through direct mergers with other large black holes or the rapid accretion of cold gas streams, while simultaneously suppressing the growth of others through fierce competition or destructive feedback. The environment seems to foster a winner-take-all dynamic that our models of hierarchical growth don't fully capture. Adding to the puzzle is the strange alignment of black hole spins. When two galaxies merge, their central black holes are predicted to eventually spiral together and combine. During this violent process, the incredible gravitational forces should, in theory, randomize the spin axes of the resulting black hole. However, observations of the powerful jets launched by active black holes in nodes reveal a startling degree of coordination. These jets, which are aligned with the black hole's spin axis, often appear to be pointed in similar directions across vast distances within the same node, as if these cosmic powerhouses have silently agreed on a preferred orientation. This coordinated spin suggests that these black holes did not form from chaotic, random mergers, but instead grew primarily through the steady, ordered accretion of gas that was itself flowing along the large-scale filamentary structure of the cosmic web, funneling material onto them in a consistent direction over eons. The nodes, it seems, are not just chaotic crash sites, they are orchestrators of order on a breathtaking scale. Perhaps the most significant discrepancy lies in the predicted versus observed merger rates. Our simulations of these dense environments show galaxies and their black holes constantly interacting, swinging past each other in a dynamic gravitational dance that should frequently lead to collisions. We should be detecting the thunderous ripples in spacetime from these black hole mergers on a regular basis with our gravitational wave observatories. Yet the observed rate of mergers seems to be lower than expected. It's as if something is preventing these cosmic giants from finally coming together. The culprit may be the very environment that brought them close in the first place. When two galaxies merge, their black holes sink to the center of the new combined galaxy. But to go from there to a final, merging embrace, they must shed enormous amounts of energy, which requires interacting with the surrounding stars and gas. In the sparse outskirts of a galaxy, this final parsec problem is a well-known theoretical hurdle. Within a node, the problem might be reversed. The environment could be so packed with other objects and so turbulent that it actually prevents the black holes from getting close enough to merge, effectively stalling them in a perpetual cosmic waltz just shy of collision. This leaves us with a node potentially filled with binary or even ternary black hole systems, circling each other for billions of years, their promised gravitational wave songs left unsung. But if the behavior of black holes at the heart of nodes seems to defy our expectations, the very light that travels to us from these cosmic crossroads holds its own set of profound and bizarre secrets. As astronomers train their most sensitive instruments on the brilliant cores of these intersections, they are documenting a series of anomalies in the light itself. Subtle, yet persistent, deviations in how light propagates through these regions that cannot be explained by any known property of dust, gas, or plasma. It's as if the space within these nodes is imbued with a strange, intangible quality that subtly alters the light passing through it in ways we are only just beginning to detect. One of the most puzzling of these effects is an unexpected level of scattering. When light from a distant quasar or galaxy passes through the immense, hot plasma of a node, astronomers can predict how much that light should be diffused or scattered by the free-floating electrons in that gas. Yet, in numerous cases, the light from background objects appears fuzzier or more smeared out than these models allow. It's not a dramatic blurring, but a consistent, subtle excess that suggests the presence of something in the intracluster medium that we haven't accounted for. This couldn't be explained by simple dust, as the temperatures are far too high for any solid grains to survive. The leading suspicion falls on a population of extremely low density, yet pervasive, microscopic structures or turbulent magnetic fields that are far more effective at scattering light than the smooth plasma we assume is there. It's akin to looking through a pane of glass that is mostly clear, but has a faint, uniform frosted quality that no one can quite explain. Even more telling are the anomalies found in the polarization of this light. Polarization refers to the specific orientation of light waves as they travel, and it can be very systematically altered when light passes through a magnetic field or scatters off of particles. By studying the polarization of light that has traversed a node, we can effectively map the magnetic fields within it. However, the patterns we see are often strangely coherent and uniform over vast distances, or show abrupt changes in alignment that don't correspond to any visible shock waves or gas densities. In some instances, the degree of polarization is either significantly higher or lower than what should be possible given the estimated density and temperature of the plasma. This points toward magnetic fields that are either much stronger, more ordered, or more turbulent than our best models of the intracluster medium can reproduce. It suggests that our understanding of magnetohydrodynamics, how magnetic fields and ionized gas interact, on these colossal scales is still fundamentally incomplete. Perhaps the most significant clues come from the light spectrum, its breakdown into constituent colors. As light journeys through space, specific elements in its path absorb characteristic wavelengths, leaving behind dark lines in the spectrum that act like a chemical barcode. When we analyze the light that has passed through a node, we sometimes find that these absorption lines are subtly shifted or distorted in ways that cannot be explained by the known velocity of the gas or its temperature. Some lines appear mysteriously broadened, as if the atoms absorbing the light are being jostled by violent turbulence or embedded in a pressure field we haven't detected. Others show anomalous ratios between different absorption lines from the same element, which is a direct indicator that the physical conditions within that cloud of gas, its pressure, density, or ionization state, are not what we have measured through other means. These spectral distortions are the calling cards of unknown physics. They could be evidence of exotic types of matter, such as a previously unknown stable of particles or a novel form of plasma that interacts with light in a non-standard way. Some theorists have even speculated that these subtle effects could be a manifestation of the quantum nature of spacetime itself, a faint signature of the graininess of the universe that is only magnified when light travels through the immense gravitational lenses of these nodes. Each anomalous wavelength, each unexpected polarization, is a piece of a puzzle, suggesting that the space within the cosmic web's brightest intersections is not merely empty volume, but a complex and active medium whose full properties and influence on the radiation that traverses it remain largely uncharted. And now we arrive at one of the most visually arresting and philosophically unsettling mysteries on our list, the strange and seemingly impossible alignments of galaxies themselves. Imagine looking out at a vast crowd of people, and instead of facing in random directions, you notice that a surprising number of them are all tilting their heads at the same precise angle. This is the essence of the large-scale alignment mystery, but on a cosmic scale. Within the dense nodes of the cosmic web, astronomers are finding that the spins and orientations of thousands of galaxies are not random. They appear to be subtly coordinated, aligned with each other and with the vast filamentary structure of the web itself across hundreds of millions of light years. This coordination defies our standard models of how the universe imparts spin to galaxies, suggesting that the angular momentum for these colossal structures was locked in place during the universe's very first moments. The statistical evidence for this is both robust and deeply controversial. It's not something you can see with a casual glance. It requires analyzing the positions and rotational axes of hundreds of thousands of galaxies from massive surveys like the Sloan Digital Sky Survey. Scientists use sophisticated algorithms to measure the inclination of a galaxy's disk and the direction of its spin. When they compile this data and compare it to the map of the cosmic web, the signal emerges, a statistically significant tendency for galaxies within the same filament to have spins that are parallel to that filament's axis. Even more bizarrely, in the dense nodes where filaments intersect, the alignments can become even more pronounced, with galaxies showing a preference for orienting their spin axes in a specific direction relative to the node's center. The probability of this happening by pure chance is astronomically low, pointing to a real, physical process that is orchestrating this cosmic ballet. This finding strikes at the heart of our understanding of structure formation. According to the Standard Model, the angular momentum of a galaxy, its spin is acquired through a process called tidal torque theory. As a proto-galaxy collapses under its own gravity, it experiences tidal forces from the gravitational pull of neighboring nascent structures. This gravitational tug of war sets it spinning, much like a pinwheel starts to turn when you hold it in a breeze. This process is inherently local and random. The torques from one direction should cancel out the torques from another, resulting in galaxies with spins pointing in every conceivable direction. The fact that we see coherent alignments on such colossal scales means that the initial conditions from which these galaxies formed were not random. The seeds of their rotation were sown on scales far larger than their own local environment, imprinted on the cosmos before the galaxies themselves even began to form. So what could have possibly set this initial universal spin? One of the leading hypotheses takes us back to the very beginning of everything, the epoch of inflation. During this period of hyper-accelerated expansion, it's believed that quantum fluctuations were stretched to macroscopic scales, becoming the seeds for all future structure. But some models of inflation also predict the generation of primordial magnetic fields or other large-scale forces that could have pervaded the infant universe. These fields, if they were coherent over vast distances, could have exerted a torque on collapsing clouds of matter, gently nudging them to spin in a preferred direction and aligning them with the magnetic field lines, which themselves would have been aligned with the nascent cosmic web. In this scenario, the alignments we see today are a fossilized record of these primordial forces, a ghostly hand from the dawn of time that still guides the orientation of galaxies. Another, even more profound possibility involves the gravitational influence of the cosmic web itself. The web is not a static structure. It is a dynamic entity through which vast rivers of dark matter and gas continually flow from the voids toward the nodes. This coherent inflow could itself impart a specific angular momentum to the galaxies forming within it. Imagine a leaf caught in a river current. It will naturally align itself with the flow of the water. Similarly, a galaxy forming within a massive filament of flowing dark matter may have its spin axis shaped by that large-scale motion, locking it into an alignment with the filament. This would represent a form of communication across billions of light years, where the overall architecture of the cosmos directly dictates the individual properties of the galaxies within it, a level of cosmic coordination we are only just beginning to appreciate. But if the coordinated spins of galaxies hint at a universe imprinted with order from its very beginning, an even more radical idea suggests that the very rules of the game might not be fixed. The fundamental constants of nature, numbers like the fine structure constant that dictate the strength of electromagnetic forces, are the bedrock of physics. We assume they are immutable, unchanging across time and space, the unwavering foundation upon which all physical reality is built. This principle is so deeply ingrained that to question it is to challenge the core of modern science. Yet, a series of astonishing and controversial observations have emerged, primarily from studying the ancient light of quasars that has passed through the nodes of the cosmic web, that appear to show these constants are not constant at all. The variations are tiny, but they are statistically significant, and they seem to be mysteriously correlated with the positions of these massive intersections in the universe. The evidence for this comes from a technique of exquisite precision. When light from a distant quasar travels for billions of years to reach us, it passes through clouds of gas and dust. Atoms within these clouds absorb specific wavelengths of this light, leaving behind a unique fingerprint of dark lines in the quasar spectrum. The precise positions of these absorption lines are determined by the values of the fundamental constants, most notably the fine structure constant, often represented by the symbol alpha. This constant governs how strongly electrons are bound to atoms. If alpha had a different value in the distant past or in a different region of space, the spacing between these absorption lines would shift by a minuscule but measurable amount. By comparing the spectra of quasars whose light has passed through different nodes at different cosmic epochs, astronomers have reported a faint but persistent signal. The value of alpha appears to be slightly different in certain directions of the sky, and those directions align with the vast superstructures of the cosmic web. The implications of such a discovery are nothing short of revolutionary. It would mean that the laws of physics themselves are not universal, but are instead shaped by the local environment, potentially by the immense gravitational fields or the unique energy densities found within these nodes. One extraordinary interpretation is that we are seeing the influence of extraspatial dimensions, a key prediction of string theory. In these models, the 3 dimensions of space we experience are just a part of a higher dimensional reality. The other dimensions are curled up and hidden, but their size and shape could influence the effective values of the constants we measure in our 3D world. The mind-bending proposal is that the titanic mass concentrated in a node could be subtly warping these extra dimensions, causing the constants we perceive to very slightly shift in its vicinity. We would be witnessing a direct leak from a higher dimensional reality into our own. Another, less exotic but equally profound, explanation involves a fundamental link between these constants and dark energy. The energy of the vacuum of space, which we call dark energy, is itself a sort of fundamental constant. If dark energy can vary, if its strength is different in different places, it could be coupled to the other constants, causing them to vary in tandem. The nodes, being regions of extreme density, would represent a different vacuum state compared to the empty voids, potentially creating a landscape where the rules of physics are minutely different. This would transform our view of the universe from a place with a single set of laws to a patchwork of slightly varying physical realities, with the nodes acting as distinct domains. Of course, the scientific community approaches these claims with intense scrutiny, and the burden of proof is immense. The measured variations are at the very limit of what our most sophisticated spectrographs can detect, and the potential for systematic errors is high. Critics rightly point out that the results could be artifacts of the instruments themselves or caused by unknown chemical contaminants in the absorbing clouds that mimic a change in alpha. The process of comparing spectra across billions of light years is incredibly complex, and even a tiny, unaccounted-for shift in wavelength calibration could produce a false signal. For every study that claims a detection, another, equally careful analysis finds no variation at all. This ongoing debate is a testament to the difficulty of the measurement and the monumental stakes of the outcome. Resolving this mystery requires more data from next-generation telescopes and independent methods of measurement. If the variations are confirmed and their correlation with the cosmic web holds, it would be one of the most significant discoveries in the history of science, forcing a complete rewrite of physics and revealing a universe far more dynamic and strange than we ever dreamed. It would mean that the constants we hold as sacred are not the foundation of reality, but merely local bylaws shaped by the architecture of the cosmos itself. The nodes, in this view, become more than just collections of galaxies. They are realms where the very fabric of physical law is woven, and where we might finally catch a glimpse of the deeper, more flexible reality that underlies our own. Now we turn to a messenger that can travel across the universe completely unhindered, a ghostly particle that rarely interacts with anything, the neutrino. Born in the hearts of stars, in the fury of supernova, and in the violent jets of black holes, these nearly massless particles fly straight through planets and stars as if they weren't even there. To catch them requires colossal, ingenious detectors buried deep underground, like the Ice Cube Observatory at the South Pole, which uses a cubic kilometer of pristine Antarctic ice as its detection medium. For years, these instruments have been patiently listening to the neutrino symphony of the cosmos, and they've begun to pick up a strange and persistent melody. There is an unexpected flux of neutrinos, a significant surplus of these ghostly particles that seems to emanate from the directions of the cosmic web's largest nodes. Yet when astronomers search for the source within those regions, they often find nothing that should be capable of such a powerful emission. This is a classic cosmic whodunit. A high-energy neutrino is a calling card of immense violence, a product of the most powerful particle accelerators in nature. When one is detected, scientists can trace its path back to a specific point in the sky with remarkable precision. The expectation is that this path will lead directly to a known cosmic engine, a flaring blazar, a recently exploded star, or a merging galaxy. And in many cases it does, but a troubling number of these high-energy neutrinos point back to the dense, crowded intersections of the cosmic web, and when telescopes across every wavelength swing to look, they find no single, obvious source that matches the energy and intensity of the neutrino signal. It's as if we're hearing a deafening shout from a crowded room, but when we look, every single person in that room is whispering. The collective murmur of the node is not enough to account for the shout we've heard, leaving us with a profound puzzle. The anomaly isn't just about the number of neutrinos, it's also about their energy. The detected particles from these regions often show a peculiar distribution, with an unexpected abundance at specific energy, ranges that don't neatly correspond to the predicted output of known astrophysical sources. This peculiar energy signature is a crucial clue, a fingerprint that could point to a new type of particle accelerator operating within these nodes. The leading theory is that we are seeing the combined output of many hidden or orphaned sources. Within a node, there could be thousands of stellar mass black holes or neutron stars that are actively accreting matter and producing neutrinos, but are individually too faint for our telescopes to see. Together, their collective output could create a powerful, diffuse glow of neutrinos that appears to come from the entire node rather than a single point. Another compelling possibility brings us back to the mysterious dark matter that suffuses these regions. Certain theoretical models predict that when dark matter particles collide and annihilate, they should not only produce gamma rays but also a fountain of high-energy neutrinos. The dense cores of nodes, acting as the universe's most efficient dark matter traps, would be the perfect place for these rare annihilations to occur. The peculiar energy signature of the detected neutrinos could therefore be a direct readout of the mass of the dark matter particle itself, a discovery that would finally crack one of physics' greatest mysteries. We would be indirectly observing the properties of the invisible stuff that makes up most of the universe's matter by watching the ghosts it produces when it decays. Yet, the answer might be even more extraordinary, pointing to engines of such immense power that they defy our current categorization. There could be a population of entirely new types of transient objects within these nodes that flare up, produce a burst of neutrinos, and then fade into obscurity before our optical or X-ray telescopes can identify them. Or perhaps the immense turbulence and shock waves that permeate the intracluster medium of a node are acting as a colossal, distributed accelerator. In this scenario, protons and other particles are being accelerated to extreme energies not by a single black hole, but by bouncing across a network of shock fronts created by merging galaxies and colliding gas clouds throughout the entire node. This would create a vast, invisible machine spanning millions of light years that constantly manufactures high-energy neutrinos without a single, pinpointable heart. Each of these ghostly particles, then, is a message from the hidden workings of the universe's largest and most powerful structures, urging us to listen more closely to the silent whispers of the cosmos. And now we venture into perhaps the most mind-bending and metaphysical of all the mysteries hidden within the cosmic web's nodes, the controversial and extraordinary idea that these vast intersections might be offering us tangible evidence that our universe is a hologram. This isn't science fiction, it's a serious theoretical proposition known as the holographic principle, and it suggests that all the information contained within a three-dimensional volume of space, like a massive node, might actually be encoded on its two-dimensional boundary. It's the cosmic equivalent of believing a stunningly detailed, three-dimensional movie is being projected from a flat, two-dimensional screen. For decades, this has been a fascinating but largely abstract concept in theoretical physics, confined to the realms of string theory and quantum gravity. But recently, some physicists have begun to argue that the specific structure and information content of the universe's largest nodes show mathematical correlations that could be the first observational hints that this principle is not just a mathematical curiosity, but a fundamental description of our reality. The journey to this idea starts with a paradox about information and black holes. When matter falls into a black hole, it seemingly disappears, taking its information with it. This violates a core tenet of quantum mechanics, that information cannot be destroyed. The holographic principle emerged as an elegant solution. It proposes that the information about everything that falls into a black hole is not lost inside its three-dimensional volume, but is instead perfectly encoded on its two-dimensional event horizon, the point of no return. This discovery by physicist Jacob Bekenstein and others suggested that the maximum amount of information any region of space can contain is not proportional to its volume, but to the area of its surface. This was a monumental shift in thinking, implying that the three-dimensional world we experience might be a projection from a vast, complex information field residing on a distant, two-dimensional surface. So how could we possibly see evidence of this in the nodes of the cosmic web? The connection lies in the way information and entropy are theorized to behave on the largest scales. The nodes are the universe's most information-rich environments. They contain thousands of galaxies, each with billions of stars, planets, and ultimately particles, all representing an almost incomprehensible amount of data. According to the holographic principle, this information should have a limit, and that limit should be defined by the surface area of the node, not its immense volume. When researchers apply these holographic calculations to some of the largest known superclusters, they find a startling and provocative match. The theoretical maximum information capacity for these regions, based on the area of their gravitational boundaries, aligns suspiciously well with the estimated information content derived from the number of baryonic particles within them. It's as if the universe itself is obeying a cosmic data storage limit, and the nodes are pushing right up against it. This mathematical correlation is the heart of the controversial evidence. Proponents of this view point to other strange holographic-like properties. The complex network of filaments feeding a node, for instance, can be analyzed using the tools of information theory. Some studies have suggested that the way information appears to flow and be distributed within these structures mirrors the way data is encoded and decoded in a holographic system, displaying a form of entanglement and non-locality that is difficult to explain with standard physics. Furthermore, the patterns of temperature fluctuations in the cosmic microwave background, the ancient light that was imprinted on the universe's surface, have also been analyzed through a holographic lens. Some theorists argue that the statistical distribution of these hot and cold spots is more simply and elegantly explained by a universe that has two spatial dimensions rather than three, as if we are seeing the fingerprints of the lower dimensional reality from which our world is projected. Naturally, this idea is met with intense skepticism from much of the scientific community. Critics argue that these mathematical correlations could be coincidences, or that they are the result of our current incomplete understanding of gravity and quantum mechanics on cosmological scales. They point out that the holographic principle, while beautiful, is incredibly difficult to test, and that attributing these patterns to such a radical cause is premature when more conventional explanations within the standard model of cosmology have not been fully exhausted. The burden of proof for claiming our entire reality is a projection is rightly astronomically high, yet the mere possibility is profoundly transformative. If the holographic principle is correct, it would mean that the nodes are not just physical structures but informational ones. Their immense gravity and complexity would be a manifestation of an underlying data processing happening on a cosmic scale. The mysterious phenomena we see within them, the anomalous gravity, the strange light, the coherent alignments, might all be different symptoms of this single, deeper truth, that we are living inside a cosmic simulation, or at the very least, a reality where the illusion of depth is constructed from a fundamentally flat, information-based foundation. To peer into a node, then, is not just to look at a collection of galaxies. It is to stare into the code of the universe itself, and perhaps catch a glimpse of the lower dimensional projector that is casting the magnificent and puzzling shadow we call our home. And now we arrive at a concept that pushes the very boundaries of cosmology and philosophy, the extraordinary idea that our universe may not be the first and only one, but merely the latest chapter in an infinite cycle of cosmic death and rebirth. This is the hypothesis of a cyclic universe, and its most tantalizing evidence might be hiding in plain sight, encoded within the very nodes of the cosmic web we've been exploring. The standard Big Bang model presents a definitive beginning, a singularity from which space, time, and all physical laws erupted into existence. But what if that event was not a true beginning, but a transition? What if our universe is one in a long series, with each Big Bang preceded by a big crunch or a dramatic bounce? If this is true, then the immense gravitational and energetic violence of those previous universes might have left faint scars or imprints on the fabric of our own, and the densest regions of matter, the nodes, are where we might have the best chance of finding them. The search for these potential imprints focuses on the oldest light we can observe, the cosmic microwave background. This fossilized radiation is our most direct window into the universe's infancy, and it should, in theory, be a nearly perfect blackbody, its temperature fluctuations random and Gaussian, shaped solely by the quantum fluctuations of our own universe's inflation. Yet, when scientists analyze the CMB data with excruciating precision, they find a handful of persistent, large-scale anomalies that stubbornly resist conventional explanation. Among the most puzzling are specific, non-random patterns in the temperature map. Certain large cold and hot spots appear with a statistical significance that makes them incredibly unlikely within the standard inflationary paradigm. It's as if the canvas of our early universe was not blank, but had a faint, pre-existing texture painted onto it before our own history even began. Some cosmologists propose these patterns are echoes. In a cyclic model, the universe does not emerge from nothing but from the collapse of a previous epoch. That previous universe would have had its own large-scale structure, its own cosmic web of nodes and filaments. In its final moments before the Big Bounce, as matter and energy were compressed to unimaginable densities, the gravitational waves and density perturbations from that ancient structure could have been imprinted onto the fabric of spacetime itself. Then, during the rebound into our new universe, those imprints would have been stretched across the sky by a new period of inflation, appearing to us today as anomalous, coherent patterns in the CMB. These wouldn't be structures in our universe, but scars on our universe, a cosmic palimpsest where the ghostly writing of a previous cosmos shows through. Beyond temperature, the polarization of the CMB offers another potential clue. The polarization patterns, or B modes, are primarily caused by gravitational waves from inflation. However, some theories of a cyclic universe predict a specific secondary polarization signal that would be the direct result of the collision of our universe with another bubble universe in a greater multiverse, or from the gravitational shock waves of the bounce itself. While the search for this specific signal is ongoing and fiercely debated, its detection would be the closest thing to a smoking gun for a pre-Big Bang cosmology, a direct fingerprint from a time before time. Perhaps the most compelling argument for a cyclic imprint, however, lies not in the light but in the darkness. The distribution of dark matter in the largest nodes of the cosmic web shows those puzzling anomalies we discussed earlier. Some are overly dense, others strangely diffuse. A cyclic model could offer a fresh explanation. If our universe was born from the collapse of another, the dark matter from that previous cycle wouldn't simply vanish, it would be recycled. But the process of collapse and rebirth might not perfectly preserve its distribution. The dark matter could have been scrambled, its halo profile slightly altered, its clustering properties changed during the violent transition. The anomalous nodes we see today, which so challenge the cold dark matter model, might not be failures of our theory, but rather artifacts of a much longer history. They could be the cosmic equivalent of heirlooms from a previous existence, their forms shaped by laws and events we can only begin to imagine. Naturally, this entire line of inquiry resides at the very frontier of theoretical physics and is met with healthy skepticism. Critics rightly argue that these anomalies could be statistical flukes, artifacts of our measurement techniques, or simply signs that we need to refine our understanding of inflation within the standard model, not throw it out for a cyclic one. The burden of proof for something as monumental as a pre-Big Bang universe is, and should be, extraordinarily high, yet the pursuit itself is electrifying. It represents the ultimate exercise of scientific curiosity, the refusal to accept a boundary, even one as seemingly absolute as the beginning of everything. The nodes of the cosmic web, having already presented us with so many mysteries, now offer us a potential window not just across space but across time, to an epoch before our own, inviting us to consider that our entire cosmic story might be just one verse in an endless, grander poem. And now we arrive at a mystery that lies at the very frontier of science and philosophy, a place where the cold, hard data of cosmology meets the deeply personal, subjective experience of awareness. This is the most speculative phenomenon on our list, a concept that many mainstream scientists dismiss as pure pseudoscience, yet one that a growing number of interdisciplinary thinkers believe we can no longer ignore: the possible and profoundly controversial connection between the structure of the cosmic web and the nature of consciousness itself. It's an idea that sounds like it's been lifted from the pages of science fiction, suggesting that the universe's largest structures might not be independent of us, but could instead be strangely entangled with the very act of our observation. This radical line of inquiry finds its roots in one of the greatest puzzles in all of physics, the measurement problem in quantum mechanics. In the subatomic world, particles exist in a blurry state of multiple possibilities, called a superposition, only settling into a definite state when they are observed or measured. But what exactly constitutes an observation? The mathematics of quantum theory doesn't say. It simply states that the act of observation causes the wave of possibilities to collapse into a single reality. For decades, this has led to a deeply unsettling question. Does consciousness itself play a fundamental role in shaping reality? The most famous proponent of this view was the Nobel Prize-winning physicist Eugene Wigner, who argued that the consciousness of the observer is the ultimate catalyst for wave function collapse. This idea, known as the von Neumann-Wigner interpretation, places consciousness not as a passive byproduct of the physical brain, but as an active participant in the creation of the cosmos. So how could this possibly relate to the nodes of the cosmic web? The connection is drawn through scale and information. the nodes represent the most complex, information-rich, and structurally coherent regions in the entire universe. Some theorists, often working at the intersection of cosmology and quantum information theory, propose that these nodes could act as natural amplifiers or anchors for consciousness. In one highly speculative model, the intricate network of filaments and nodes mirrors the neural networks of a human brain, suggesting a form of cosmic-scale intelligence or a universal mind. The idea is that consciousness might not be confined to biological organisms, but could be a fundamental property of the universe, much like mass or charge, and that it would naturally coalesce and express itself most strongly in regions of maximum complexity and integration, the cosmic nodes. Another controversial proposal links the observer effect in quantum mechanics directly to the universe's large-scale structure. The concept, sometimes called cosmological quantum consciousness, suggests that the act of conscious observation by beings within a galaxy inside a node could have a retrocausal effect, influencing not just a single particle, but the very history of how that node formed. It's a staggering notion that our present-day observation of these colossal structures could be, in some minuscule way, necessary for their very existence in the past, tying the development of the cosmic web to the eventual emergence of conscious life within it. This resonates with the anthropic principle, the idea that the universe's laws are fine-tuned for life, but takes it a dramatic step further into the realm of active participation. Naturally, these ideas are met with intense skepticism and often outright derision from the majority of the physics community. Critics rightly point out that this is a classic example of a God of the gaps argument, inserting consciousness into a place where our current physical models are incomplete. They argue that attributing wave function collapse to consciousness doesn't solve the measurement problem. It just pushes it back a step to the even more mysterious question of what consciousness is. Furthermore, the comparison between the cosmic web and the human brain, while visually striking, is largely an analogy based on superficial structural similarities, with no established physical mechanism linking the two. The neural networks in our brains are shaped by electrochemical signals and Darwinian evolution, while the cosmic web is shaped by gravity and dark energy processes that operate on entirely different scales and principles. Yet, despite the valid criticisms, the persistence of these ideas speaks to a deeper, more profound yearning in the human spirit. We look out at a universe that has, against inconceivable odds, given rise to beings capable of contemplating it. The cosmic web's nodes are the great gathering places of galaxies, and we find ourselves on a planet orbiting a star in one of those galaxies. Is it pure coincidence that the universe's most complex structures and the only known examples of conscious observation exist in the same locations? Or could there be a deeper, yet to be discovered connection between the architecture of reality and the experience of being aware of it? While the answers remain far beyond our current grasp, the question itself forces us to consider our place in the cosmos not as passive inhabitants, but as potential participants in an unfolding story of astonishing depth, where the act of looking out at the stars might, in some small but fundamental way, be a part of what called them into being. From the ghostly whispers of missing matter to the universe-shattering possibility of a holographic reality, the 25 unexplained phenomena within the cosmic web's nodes present a breathtaking tapestry of mystery that defies our deepest scientific convictions. We've journeyed through gravitational anomalies where dark matter refuses to follow its own rules, witnessed the explosive paradox of gamma rays with no known source, and stood before ancient, impossible structures that materialized far too early in cosmic history. We've grappled with the spooky suggestion of quantum entanglement on a billion light-year scale, been bewildered by the sudden appearance of perfect celestial rings in the void, and confronted the unsettling evidence that the universe's expansion rate might not be constant after all. We've seen time itself behave erratically under immense gravity, felt the presence of magnetic fields of impossible size and strength, and listen to the gravitational wave hum of the cosmos that mysteriously harmonizes with the web's largest structures. The journey revealed galaxies flowing in inexplicable unison, a perplexing shortage of dwarf galaxies, and a chemistry within the nodes that doesn't match the universe's standard recipe. We followed the trails of ultra-high-energy cosmic rays back to their node-based origins with no visible engine to power them, explored the active influence of nothingness as cosmic voids push and shape the somethingness of the nodes, and even dared to look for the faint, pixelated shimmer of quantum gravity in the fabric of spacetime itself. The enigmas only deepened as we examined the strange statistics of supermassive black holes, the subtle distortions of light that hint at unknown properties of space, and the awe-inspiring, coordinated spin of thousands of galaxies pointing to a primordial order. We confronted the radical notion that the fundamental constants of nature might not be constant, tuned into the mysterious neutrino song emanating from hidden sources, and ventured into the most metaphysical realms with the staggering proposition that these nodes might be evidence of a holographic universe, a cyclic cosmos, or even a reality intertwined with the very nature of consciousness. Collectively, these are not minor puzzles to be solved with a simple tweak to an equation. They are fundamental challenges to the pillars of modern physics, to our understanding of gravity, the nature of matter and energy, the behavior of time, and the very laws that govern reality. Each mystery is a thread pulling at the fabric of our standard models of cosmology and particle physics, suggesting that a profound paradigm shift is not only coming but is necessary. These nodes are the universe's grandest experiments, nature's own way of conducting physics at energies and scales we could never hope to replicate, showing us where our current knowledge ends and the true frontier of discovery begins. This is where the conversation turns to you. After this voyage into the deepest cosmic unknowns, which of these 25 phenomena captivates your imagination the most? Does the sheer impossibility of the universe's earliest giant structures spark your curiosity? Or does the mind-bending potential of quantum connections across space speak to you? Perhaps the controversial hints of a holographic reality or a cyclic cosmos feel like the most transformative possibility. Share your thoughts in the comments below on which cosmic puzzle you find most intriguing and what you believe could be the key to unlocking its secrets. Your perspective is a part of this ongoing human quest to look into the darkness between the stars and not only see the light but to finally understand it.